Today we're going to do something a little different. We're not just going to memorize one of the most famous equations in all of science, we're going to build it from the ground up, piece by piece. Think of it like a puzzle. Let's get started.
So let me ask you a question. What could a scuba tank, a bunch of birthday balloons, and the tires on your car possibly have in common? I mean, they seem completely different, right? Well, it turns out they're all connected by one single incredibly elegant scientific relationship, and you're about to understand exactly what that is.
So here's the game plan. We're going to construct the ideal gas equation from scratch. We'll look at a few basic, common sense laws, see how they fit together, and then snap them all into place to create the final, super powerful formula.
All right, let's grab our first piece of the puzzle. This one is all about the push and pull between the pressure of a gas and the amount of space or volume it takes up.
Okay, so this is what's known as Boyle's law. And honestly, it's something you already know intuitively. Just picture squeezing a balloon. The more pressure you apply with your hands, the smaller the balloon's volume gets, right? And when you let go, less pressure means more volume. They're what we call inversely proportional. One goes up, the other has to go down. The only catch is the temperature has to stay the same. And you know what? The math for this is beautifully simple. It's just pressure times volume equals some constant number. We'll just call it K for now. This P times V relationship is our very first building block. Solid. Let's get the next one.
Okay, piece one is in place, pressure and volume. But what happens when things heat up? I mean, temperature is obviously a huge deal when it comes to gases, and it's the next critical piece of our puzzle.
And that, my friends, is where Charles' law comes in. It says that if you keep the pressure the same, the volume a gas takes up is directly tied to its temperature. And this just makes sense. When you heat a gas, its little molecules get a ton of energy, they start zipping around like crazy, and they push outwards, making the whole thing expand. It's exactly why a hot air balloon rises. You heat the air, it expands, and up it goes.
So how does that look as a formula? Simple again. Volume divided by temperature equals another constant. So now we've officially connected volume and temperature in our puzzle. We're getting really close, but there's one more essential piece we absolutely need. So we've got pressure, we've got volume, and now we've got temperature. But what about the actual amount of gas we're dealing with? To finish this thing, we need a way to account for how much stuff is actually in there. And in chemistry, we use a unit called the mole. Don't let the name scare you. Just think of it as a specific, very big number of molecules, the same way a dozen just means 12. And this leads us right to Avogadro's law, which is honestly the easiest one to get your head around. It just says that if you keep the temperature and pressure steady, the more gas you have, the more space it takes up. That's it. If you blow more air into a balloon, it gets bigger. More gas, more volume. See? Simple. And yep, you guessed it. There's a formula for that too. Volume divided by N, our symbol for the number of moles, equals a constant. And just like that, we've collected all of our puzzle pieces. Now it's time for the really fun part, the final assembly. All right, this is it. This is the moment we've been working towards. We have our three separate laws, our three puzzle pieces. Now let's see how they all snap together into one beautiful, unified equation. Let's just walk through it. From our laws, we know that volume gets bigger as N, the amount of gas gets bigger. We also know it gets bigger as T, the temperature gets bigger. And we know it gets smaller as P, the pressure gets bigger. So we can just mash all of that together into one big relationship. Volume is proportional to N times T, all divided by P. It's amazing how they all just fit. Now, to turn this proportional to sign into a real equal sign, we just need one little thing. It's a special number called the universal gas constant, and we just call it R. We slot that in, do a tiny bit of algebraic shuffling, just multiply both sides by P, and bam, there it is. PV equals nRT, the ideal gas equation. We built it. So let's do a quick recap of our masterpiece here. P's for pressure, V's for volume, little n is the number of moles, how much gas we have, T is the temperature, and you gotta make sure it's in Kelvin for the math to work, and R is that magic constant that holds it all together. The coolest part is, as long as you know any three of these, you can always solve for the fourth. It's incredible. And that's really the magic of what we just built. This isn't just some random letters and numbers a teacher told you to memorize. It's a single, compact tool that describes how almost any gas behaves under all sorts of conditions. From those scuba tanks to birthday balloons, this is the secret connection. So there you have it. We took a few simple ideas and built the ideal gas equation from scratch. But did you catch that one word? Ideal. This equation is perfect for a perfect hypothetical gas. And that leaves us with a really cool question to chew on. What makes the real